All right. I want to give, so that's the official title here, Surrogates for UQ and Robust Design, an aerospace example. In the end, it's going to be 2 examples, one for a forward propagation and one for robust design. So when I speak about forward uncertainty quantification, pretty much if we wrap everything we have seen on the surrogate in one nice representative plot, this is what you get. You do have a black box model here on the right, and then you do surrogate based uncertainty quantification by running a few black points, do some infill, and then get some continuous representation of the quantity of interest you're interested in. As I said, I'm an aerodynamics guy, so we're going to look at some aerodynamic examples, and the quantity of interest is drag or pressure distribution. You can propagate that forward to range equation, whatever you like. But before we start with this, I always said, yeah, you take the inputs and then you move it to the outputs. And if you're at this point, you realize, yeah, what's the input? So we're thinking about, let's do a forward propagation for an aircraft. And let's ask Airbus what they think about some reasonable distributions for all these values. They didn't share too much. Maybe we asked the wrong people. So what we did is, what you do nowadays, you Google, and we find OpenSky, which is actually quite nice. So it's an open website where you can take a lot of information from. It pretty much tracks flights and puts all their information on there. And we decided to go for something like altitude, Mach number, and lift coefficient. Like the Mach number, you can directly take from the corresponder on the aircraft, and then lift coefficient pretty much correlates to the weight. So no, there are not always the same number of passengers and other things on it. It's a bit tedious to get it out of these data. In the end, we wrote a script that pulls the data from there and transforms it. In the end, from an aerodynamic point of view, it influences the aircraft angle of attack that you need to generate enough lift to not fall from the sky. These ones here are all A330 flights, if I'm not mistaken, from Heathrow to Dubai over a period of probably 3 months, not entirely sure. And then we take this and we say, let's get some probability density function out of this that we can then propagate through our model. As we were interested on cruise performance, the first thing we did is we filtered cruise Mach number out of this. We did it equivalent for the other conditions. Once you have this, you can already see there is quite a huge spread, and definitely not the one line where the aircraft manufacturer initially gave as cruise conditions. And if you do this, you can see each color bar here is a different airline. You can see some are notoriously late and flying faster, while others are not. You can guess yourself which one is which. But definitely, I think the design Mach number, let's put it here for the sake of it, you're definitely having a variation around it that you're not accounting for, which has an influence on the performance that you sell later on, and which has an implications of customers getting back to you and saying, look, I use it in my everyday routine, and it's somehow different than what I expected. So, and then we kind of combine these into a PDF for the Mach number. That's not the actual one. You will see it on the next slide. So we use this as a starting point, and then says, as the task, let's propagate this uncertainty in cruise condition to aerodynamic quantities of interest using a CFD solver. Let's take a look at the XRF1 configuration. Probably most of you are familiar with this. If you are not, it's an Airbus-provided research configuration. Yeah, we use the CFD simulations running the DLR tau code and an HPC system, so it takes a few hours to do one simulation. I think it's supposed to be representative of a long-range aircraft configuration, and the Airbus shares it with a lot of partners. Probably some of you have been in touch with it. And we take the operational uncertainties that we derive from the OpenSky website, as you have seen before. There is a certain spread in Mach number, in lift coefficient as well. And altitude is quite interesting because you can see the flight levels here, and it does have an effect on the Reynolds number at the end of the day. So if you do this, you have the operational uncertainties. You have the surrogate-based uncertainty quantification framework, let's call it like this. And then you move it forward, and this is what you get. So definitely you can see there is a drag distribution, and it's no longer a single value. And it's even non-Gaussian at the end of the day. So that would be probably the scalar value that you would tell someone. In a worst case, you're here. In a best case, you're here. In a worst case, you're probably somewhere around here. But you can also, as you did CFD, dig deeper and take a look into the pressure field, like you can see here on the mean, say the mean is probably quite close to what people designed it for, actually, at the end of the day. But there is a standard deviation around the mean, where you kind of would expect it from an aerodynamic point of view around shocks. And notably, there is a large deviation here on the outboard wing. If we think about some modern concept like moving wing tips or a flexible wing tips, that's definitely where the difference in usage of the aircraft later on has the largest impact. I'm not sure what to do with it, but at least you're able to see it and take a look at it right now. And here you can also draw some realizations. So this is pretty much all the pressure profiles you can find over the envelope, and they vary quite a lot. And with it also loads and other things vary, even though loads and crews are probably not the most relevant ones. Nevertheless, you can see that this tool here allows you to provide insight into the tools you have at hand and do a forward propagation. So we were quite pleased with this and thought, okay, as a framework, it kind of does the job, and this is what we're looking for. You can increase the complexity. You can now do fluid structure coupled simulations. You can move it all the way up to Bridgie or to the range equation, also taking propulsion into account. That's probably limitless, but yeah, this is where we are right now, also in terms of complexity. And now I want to add something else to the mix. We spoke a lot about safety factors and how UQ can help with safety factors. And I want to speak about robust design for a bit. And what I mean with that is accounting for uncertainties during optimization, which is not going in the direction of reducing safety factors, but it's another perspective where UQ can add added value to your design process. The idea is you have the same thing as before, and you pretty much add a global optimization around it. And instead of optimizing minimum drag at a fixed condition, you minimize the mean of the drag over your input PDF at the end of the day. So you say, look, I know my airliners are going to use the aircraft in this range of Mach numbers, and I have a spread of the drag coefficient that we've seen on the slide before. Can I reduce the mean of the drag? And can say, if you use it as you used it before, in average, you're going to use, or you're going to have less fuel consumption than before. So that's the overall idea and the mindset behind it. You can also go for something like quantiles and say, it never gets worse than this or that. That's up to the engineer to define. So what I'm going to speak about is robust design of a natural laminar flow airfoil. Natural laminar flow has been around for years and years. Sometimes it's more popular, sometimes it's less popular. If you're not familiar with the concept, the idea is that you keep the boundary layer around the aircraft in a laminar flow state, and it transitions to turbulent later. While you're in laminar state, you have less drag than in the turbulent state. So that sounds pretty simplistic. And you would say, why are not all aircrafts laminar? Because it's not that easy to keep it in this laminar state. And operating conditions have a huge impact on laminarity. So the idea was, can we use this robust formulation to get a more robust natural laminar flow? Natural here means there are no active devices. So it's purely given the right shape, getting laminar flow. So the idea is, in the deterministic problem, minimize the drag. There are some safe design parameters. You have a fixed flight condition. And then you have these NTS and NCF values. In the end, they define where transition occurs. There are hand-calibrated values out of knowledge. And the higher the value you have, the lower or the later transition occurs. The lower the value gets, the earlier transition occurs. As you guess, as these are hand-calibrated, these are the ones which are uncertain at the end of the day. So if we start with a airfoil, which is definitely not laminar flow, but a typical transonic airfoil, we expect that the optimizer should be able to come up with a laminar configuration because it's able to predict transition from laminar to turbulent. And if you do this and do a deterministic optimization, here you can see the NTS, NCF curve. In fact, all these dots here are experiments, and we kind of put a middle line curve through this thing. It's apparently the way you do it nowadays. So you get some NCF and NTS value here. Here you can see the laminar airfoil. It has a shape that looks like a laminar airfoil. It has a long region here with increasing pressure or decreasing pressure, actually causing transition at 0.6, 65, something like this. And then you can see here at each of these points on the airfoil, you compute the critical factor, you set some limit, and transition pretty much occurs as soon as this dashed line here crosses these solid lines here at the bottom. And you can see nothing happens here, and at some point it happens there at the very back. Now, next step is, yeah, if we not make this assumption out of this black line here, but instead say, yeah, everything is equally likely in this region, we don't know, we get an uncertainty uniform distribution on these both factors here, and you can already see where the problem is. There is a critical M factor where transition pretty much occurs here, and you shift it from 60% to 5%. So essentially, you designed an airfoil which is turbulent and even a bad one. So if you draw a few realizations, you can see you either have a good one or you do have a very bad one. And I believe that's one of the reasons why people say, maybe not the best idea. So in the next step, we said, look, can we do optimization for the mean of the drag coefficient if we directly account for this? That's the deterministic result you have seen before. That's the robust result. As you can see here, if you reduce it to 6, you're still here at 0.4, 0.45. So there is a significantly larger region where you have laminar flow. If you take a look at the airfoil shape, there is not a huge difference between them. So doing this by hand is a tedious process, and that's how people would traditionally do this. They would suggest the pressure distribution and try to match a shape that fits the pressure distribution. So if you take a look at the violent plots here, you can see in the nominal condition, the deterministic optimum is still better than the robust one. However, you manage to decrease the tails here, and here it's quite significant, because here you got laminar flow, here you got turbulent flow. Well, here you pretty much always get laminar flow. In a few very rare cases, you did not get laminar flow. So at the end, you get 11.4% reduction in average drag using the robust formulation with respect to deterministic. And I just wanted to show one final bit here. If you compute the critical point where transition occurs on all of the surface locations from 5%, 10, 15, 25, 55, and so on. If you do the deterministic optimum, this is how it looks. Now, if your factors are decreasing, you kind of shrink this curve here, and pretty much all of them simultaneously will become turbulent. While here, with the robust optimization, they're pretty much perpendicular to this line, so you kind of a slow decrease in the laminar region. Now, kind of looks like this. So now the question is this a surprising result? Not really. If I go around DLR floors and ask our experts on natural laminar flow, they pretty much tell me, yeah, this is the way how you have to do it, and this is the result how you ensure this. The thing why I'm still thrilled about this was done from a student of mine who spent 2.5 months at Airbus, who had zero idea about laminar flow before, or simulating it, or even optimizing it whatsoever, but he still found the result that other experts by hand found after 15 years of trial and error. So he's not any smarter, he was just faster. He had no idea how to understand these results. Nevertheless, these methods on simply optimize the mean of drag allowed him to find a known, physically meaningful solution in a very short amount of time, which I believe is some added value to start with, especially for configurations that you're not familiar with. So I do like this result a lot, not because of the airfoil, but because of the process that allows you to do something. Yeah, and with that, I'll come to a few concluding remarks. So we've seen that surrogates are an efficient tool to perform UQ for computationally expensive black box problems. For some of them, probably the only way of doing it whatsoever. So there are a large number of different surrogate types available. Pick the right tool for your job. I can only stretch this. If you're about to select a surrogate, spend a day or two thinking about what's the surrogate I want. If you're uncertain, ask someone. Optimization accounting for uncertainty can yield advanced designs because you already incorporate the knowledge on the uncertainty. And then sensitivities can be a powerful tool to get further insight. I have not shown it today, but I thought about adding it anyway. So if you get an understanding what's the driving factor, it's even more worthwhile to your design. There are plenty of different sensitivity measures out there. Also, they are pick the right one for your job. And with that, I'm finished.